And on behalf of Simulations Plus, I welcome you to today's webinar, which will focus on the new features and capabilities in GastroPlus 8.5. Viera Lukachova, Team Leader, Simulation Technologies, will be presenting today. An opportunity to ask questions will follow Viera's presentation today. You may either send your question using the questions pane on your control panel, or you may ask your question directly using the hand-raising icon. If you're using a telephone to listen to the call, please be sure to enter the unique audio PIN displayed when you join the call. When you enter your audio PIN, this enables us to unmute your line so that you can be heard. This webinar is being recorded for playback at our website, www.simulations-plus.com. It is now my pleasure to turn the presentation over to Viera. Viera?
Thank you, John. Good morning, good afternoon, everyone. Thank you all for joining us for this presentation, which is focused on introduction of the new features that were added to version 8.5, released just last month. Many of you might have seen already bits and pieces of this presentation. Some of the features may already know about, but hopefully we'll find the others interesting just as well. The major features that were added in version 8.5 are related to the new treatments of the precipitation, PBPK and metabolism module expansions, and we've also added few general, more of a user convenience features. Starting off on the precipitation model, we've added the mechanistic precipitation model, which is based at the moment on the publication by Lindfors, and includes right now includes only homogeneous nucleation. We are aware of additional publications suggesting the process of heterogeneous nucleation, as well as suggesting different ways of accounting for the precipitation using kinetic models and so on. Those may be added in future versions. At the moment, we have included the homogeneous nucleation and using the diffusional model as proposed or as published by Lindfors back in 2008. Just briefly, the equations are shown here that account for the formation of the nuclei, and I'm not going to go through the exact equations in detail. The one parameter, the one additional parameter that it requires from the user input is the interfacial tension. The remaining parameters like diffusion coefficient, solubility, you would have been already entering for other purposes in GastroPlus. It includes a couple of optimizable or adjustable parameters, and that is this effective radius and exponential correction factor. And what they mean, especially this new radius, the theory proposed by Lindfors was that the precipitation may be driven by two processes. One, it may be driven mainly by the diffusion of monomers from the bulk solution to the surface of the forming particles, or it may be driven or dependent mainly on the integration of these new monomers to the surface of the generating particle or the growing particle. And if it's driven only by the diffusion, it's a fairly simple equation for the precipitation, really driven by the diffusion concentration gradient between the concentration in bulk water and the solubility. But once the integration factor comes in, or the process of integrating the new monomer to the surface of the forming particle, they've added additional term, including this critical radius and effective size, or this parameter of the effective size, lambda. The critical radius is something that is being generated by the equations. So the equations account for the particles coming together, breaking apart, and account for the dynamics of the motion of the particles as they are coming together and breaking apart until they form a stable first new nuclei. And that the size of that first new stable nuclei refers to the critical radius. The parameter of the effective size allows you to distinguish between the processes of that drive the formation of the new nuclei, whether it is a diffusion, if the critical radius is much higher than this effective size, then the precipitation is controlled mainly by the diffusion. When the effective size becomes larger, then the precipitation is controlled mainly by the integration of the particles on the surface of the new particle, or integration of the monomers on the surface of the new particle. The hope in generating or in adding this new model was that it would allow for more straightforward translation of in vitro measurements to in vivo predictions. And we've tested this theory. One of the compounds here shown is the published data on AZD0865, where we had the data from the transfer assay, where a solution of the compound is being added to a environment or to another buffer with lower solubility. So the compound will be increasing the concentration in the new buffer until it reaches the breaking point and starts precipitating. And by fitting the equation, we obtain the estimates for the effective size for lambda parameter as well as for the exponential correction factor. And we're trying to do a prediction of in vivo behavior of that compound using the same parameters. As you can see, it did not predict the in vivo behavior so well, so there is still some other process that needs to be accounted for aside for from these two parameters, because using simply the same values for the parameters as obtained from the transfer assay, the precipitation was quite a bit over-predicted. As shown by this red line, a lot of precipitation was happening, which would result in much lower exposure than was actually measured, shown by the points here. By adjusting one of these values in this sample, simply adjusting the exponential correction factor, we were able to match the CP time profile again. So there is a potential for allowing additional flexibility or giving additional mechanistic explanations, but it's still not as straightforward as we would like it to be. As for the outputs from this model, you will of course continue getting the amount dissolved versus time, but in addition to that, you get also the view of the details of the precipitation. So you'll get to see, or the output includes what was the size of that first radius that was formed, at what time it was formed, what was the supersaturation at the time when that first radius was formed, as well as the compound was coming from the previous compartment, the supersaturation was growing, showing what was the maximum supersaturation, what was the radius of the particle at the maximum supersaturation, and so on. So we do show you again, just like with just about any other process in GastroPlus, the details of the simulation or the details of the process as it is happening. You of course can plot the total amount precipitated in the system, shown in the red on this plot, but you can also see or explore the details in each of the compartments. So for each compartment in the gastrointestinal tract, you can plot the amount of precipitate as it's being formed and moving through the intestinal tract, the number of nuclei, again, as they may be getting formed in each compartment or coming from the previous compartment leading to the next one, as well as how the radius of the nuclei is changing throughout all of these processes. So to sum this up, these processes are important concepts, especially for formulation of poorly soluble APIs. We do recognize the importance of being able to properly model or properly account for these processes. That's why we are investing in doing research in this area, and especially in exploring how in vitro assays could be translated into prediction of in vivo behavior. And the simple first-order methods based on the simple precipitation time that you had already available in GastroPlus for quite some time have proven useful in understanding of what's happening in vivo. But the mechanistic nucleation gives you a little bit more details. As I already shown, there is still some discrepancy in trying to do a pure prediction from in vitro experiments to in vivo conditions. So there are still some additional processes which are not accounted for, but I think we are moving in the right direction in getting better handle on these processes. Next feature that was implemented was looking at the transporter in vitro to in vivo extrapolation. As you all know, there is a very good strategy for predicting metabolic clearance based on in vitro experiments, but this has not been so well established yet for the transporter effects. There have been a number of approaches in the past few years published on suggestions on how to extrapolate from in vitro experiments to in vivo behavior of the compounds with respect to interactions with transporters. And the general consensus of these approaches was that it requires some additional empirical scaling factor. But what we've noticed also that there was one common feature was that they would really account or focus only on the processes in gut or in liver, and would not consider how possibly the low permeability of the compound may be affecting the distribution to other tissues. So very commonly you might be seeing a PBPK model with all tissues treated as a perfusion limited or flow limited model, and only gut or liver were treated properly as permeability limited tissues, accounting for slow passive diffusion and incorporating the transporters. So we are suggesting to account for the slow diffusion even in the tissues where the transporter is not effective, just to account for the dynamics of that slow passive diffusion. And to make it easier to do this extrapolation, we introduced a new parameter called specific PSTC, or specific permeability surface area product, which is a permeability surface area product per milliliter of cell volume. And as such, it becomes purely a drug-dependent property, and based on the physiology, on the tissue sizes, on the extracellular and intracellular volume fractions, we can then calculate the PSTC values for each individual tissue. And that would make the extrapolation from in vitro to in vivo assays fairly straightforward. You are probably familiar with our metabolism and transporter unit converter, even though most often you may be using it for conversion of metabolic Km and Vmax values, but at the same rate you may be using it also for the conversion of transporter processes or kinetic parameters. So this is an example of published data from Roche group in 2009 of in vitro measured Km, Vmax values, as well as diffusional clearance, the passive diffusion clearance. So taking these parameters, plugging them into our converter, we obtain the in vivo estimates of Km, Vmax values, as well as the specific PSTC value. When clicking the transfer button, you get your Km, Vmax values back into the transporter table, and at the same time, the program exports the specific PSTC into the PBPK model. Then if you select the option to use this specific PSTC value, the program will be automatically calculating the permeability surface area product for each of the tissues based on this specific value and the tissue sizes, or meaning the volume of the tissue and the fraction of extracellular space in the tissue. This is an example of the performance. You might have seen this. It was actually presented in a poster in 2011, where by simply taking the in vitro data measured in rat hepatocytes and human hepatocytes, we were able to get a direct prediction of CP time profiles after IV administration in rat as well as in human. And this method did not require any additional empirical scaling factors. It was really just taking the in vitro values and the typical PBPK physiologies to predict the performance or predict the exposure in vivo. Of course, for successful application of this method, you do need proper input parameters from your in vitro assay. So you do need to make sure that from in vitro assay data, you are analyzing or trying to estimate not only Km and Vmax values, but also the parameter for that passive diffusion through the cell membranes. And additional question that we quite frequently get with respect to this diffusional clearance or to this specific PSTC value, if we cannot get that estimate from the in vitro assay, is it possible to scale it from preclinical species, for example? And the answer would be yes, under the assumption that the types of the cell membranes and the composition of the cell membranes across in given tissue is similar enough across different species. And this is an example of tobramycin simulation. And again, some of you might have seen previously the results of the human simulations with this model. And now we've expanded it and looked at would we be able to model with the same assumptions, with the same specific PSTC value, also data in other species. And I did manage to find the CP time profiles in rat as well as in dog. And as you can see, all the simulations are very reasonable. In fact, the process of the simulations was starting from the rat to obtain the value for that specific PSTC, then plugging it into the dog to verify that it still works reasonably well, and then coming back to the human to try to predict the PK in the human. And all of these simulations are really using just the default PBPK physiologies, since this compound is cleared mainly by renal secretion. The clearance was simply set to a few p times GFR, and all simulations use the same specific PSTC value. And the physiologies took care of scaling it and estimating the permeability surface area products for individual tissues in each of the species. Continuing on the improvements in enzymes and possibly the PBPK module, we've incorporated new default enzyme expressions, and these include UGTs. Based on the published information, we were able to include the UGT expression levels in human liver, kidney, and gut. We also had information on sulfotransferases in liver, kidney, and lung. And again, there was a publication coming out of a Roche group a couple of years ago on the dog expression levels, analyzing the expression levels of CYPs in dog liver as well as in gut. So those are all now incorporated as default parameters within GastroPlus. With the addition of new types of the enzymes, expanding to cytosolic proteins, which are the sulfotransferases, also adding new expression levels in different species in dogs. These, of course, required different parameters for the conversion factors. Milligrams microsomal protein per gram tissue for the microsomes or for the conversion of data from dog, or milligrams of cytosolic protein when you are trying to convert the in vitro data from sulfotransferases to in vivo. Again, you would need different conversion factor. So those are now incorporated in the metabolism and transport the units converter, where you can select the physiology and the tissue, and if we know what the proper conversion factor is for the given type of the protein, either microsomal protein or a cytosolic protein, the program will use proper value for that. As you can see, the list is expanding for which we have these conversion factors. It's not complete yet, doesn't include all the tissues, all the species yet. So in the cases where we don't have proper value, where we're not able to find yet proper value for that conversion factor, an example here shown for rat, for example, we don't have a built-in default value for milligrams microsomal protein per gram tissue. In that case, you will see this icon showing up, and by clicking on that icon, you will get an explanation which value, which conversion factor we don't have yet, and what we are using to substitute for now. So we do try to incorporate the additional conversion factors, additional parameters, but also try to make sure that for the cases where we are making approximations, you are well aware of the approximations that we made. The last large item, especially addition of on the PBPK part, was addition of infant physiologies. For those of you who have been used to using GastroPlus PBPK module previously, you were aware of the fact that for human, you were able to generate pediatric physiologies down to 1 year old, but we did not have proper algorithms to account for the first year of age, just because of the quick changes in the physiology. It required additional research to figure out how the physiologies are changing, and also to figure out how not only age, but also time of birth affects the changes in the parameters. Now we have finally added this feature as well. So now you can generate the physiologies also for infants and go for as young as 16 weeks premature newborns. So that's the youngest age that we can account for right now for a baby born after only 24 weeks of gestation. And these physiologies account, of course, for changes or for growth of the entire body and individual tissues. And for a lot of tissues, actually, we found that the in utero development is very nicely linked to the development or growth of the tissues after birth. So for a lot of tissue sizes, and the liver and kidney are shown here as an example, we were able to simply generate a relationship of the size of the tissue just based on postmenstrual age, and we're able to get a very good match to the observed or to the reported sizes of the tissues. For some parameters, like hematocrit, glomerular filtration rate, fat mass, body fat content, it's not only about the total postmenstrual age, but the birth can create a significant change in the rate of the development. And the example shown here is for hematocrit, where if you look at the red points, these were measured hematocrit within 6 hours of birth. So that's nicely showing how the hematocrit is changing during development in utero, and you can see that it's a very nice steady increase up to 40 weeks full-term birth. However, for the afterbirth, for the first 30 days, there have been observed a steady decline in the hematocrit. And this was observed regardless of the time when the children were born. The examples shown here are babies born after only 28 weeks of gestation, 32 weeks of gestation, and 39 weeks of gestation. And eventually, after that first month, after first about 30 days, you will see that the hematocrit starts again increasing until it reaches the adult values around puberty. So that all includes, all of these changes are included within the algorithms used by GastroPlus, by the per physiology in generating the physiologies for different ages, accounting for also premature birth of those babies. We did include also effect of age on tissue compositions. And you can see here the postmenstrual age goes out to about 900 weeks, which would be adulthood about 18 years old. So for these, we actually included not only for infants, but we've made changes also for older ages, for the children up to adulthood, where the newly generated physiologies will be now accounted also for changes in the tissue compositions. Only 2 tissues are shown here, but it is accounted for all the tissues as well. You can see the details of that in GastroPlus manual. With the changes to physiology,